Well, here's what we have coming up. Yes. Okay. Yeah, I'm going to keep assigning homework, but I'm not collecting it anymore. So it's up to you. But I'm just trying to suggest the stuff to do to get ready for the exam, basically. So you can take my suggestion or not. You know. Um, all right. And what do we have coming up? We have today. We have the last quiz. Quiz whatever. But that's not saying maybe there's a quiz. There definitely is a quiz. And then our final, I think, is Wednesday. Does that sound about right? Wednesday at 2? I should have looked that up. Okay. I'm crowdsourcing this. So Wednesday, 5, that would be 9. Is exam 5. And I don't think so. Oh, I see. I'm going to have to go back and look at my notes on that one. I'm not fully willing to commit to that one yet. And and then that's it. Great. So back to seminar mode. No homework questions. So let's talk about pressure. That has been my recent trend. The recent trend.
I like that
trend. But actually, this quiz is just 4 questions, so I can't really answer. Yeah, just 4. Couldn't think of another one. Okay, so pressure vessels.
How many questions was there to choose from? Yeah. Suppose I would change each time you asked it.
That's true. Pressure vessels. And I guess we are going to assume that these always have thin walls, so that's important. And we're going to deal with spherical ones and cylindrical. Yes. Although, yeah, well, let's think about that when we get there. It definitely applies to the sides of it. As far as we'll have to think about that when we get there. I've never really seen calculations of the stresses in the sides, which makes me think that maybe those stresses are not as much of a concern as the sides. Mm-hmm. Yeah, right.
Well, submarine is pressure from the inside of going outward.
It's both. Yes, you can. We will do an example of something submerged underwater, and what's going to matter, like when you go to Newton's laws, is going to be the sum of the forces, and so yeah, you can add and subtract the different pressures. Okay, so spherical. And so the pressure is like this, and then cylindrical. And at some length there, and the pressure, again, is just out onto the surface at every point. I literally have a page of notes that says that. Okay, so let's do spherical first.
So like, mostly blank page or like
For some reason, I thought that was important. Like, what if I forget what a sphere or a cylinder is? Yeah, exactly. It is, yeah, especially when you first are doing this. There's no worse feeling than being up there and realizing like your notes are wrong or you don't know. There's nothing worse. But anyways, okay, so what we're going to do for this calculation is, so we have a sphere, and we're going to imagine slicing it. So we're going to, and then we're going to do a free body diagram of one of those hemispheres. And that means that the free body that we're isolating includes half of the sphere of fluid inside. Okay? So free body diagram. Looks like, well, this isn't really a free body diagram, I guess, but the free body that we're isolating is like this. And it includes all of the fluid here. How do I want to show that? So the fluid is included in this half. And so now I'll do a free body diagram. And let's take a side view. And think about the forces that are acting. Okay, so forces are acting on this free body. Yes, the pressure, so the fluid pressure that's always a pushing force. And so the fluid that we've eliminated, that we're not considering in our free body, is pushing on the fluid that we are including. And so we have a total force here that's equal to the pressure times the area inside the, I'll call it area in. Okay, so that's pushing out. And this thing is in equilibrium. It's not exploding or anything in this case. So then we have the force applied by that pressure balanced by a tension force in the material surrounding it. And so this is equal to the tension in that material times the area of the outer part. Okay, so if we look at the front, so this is straight on to the cross section. this is the inner area. And this is the outer area. No, it's just of this slice. So it's just exactly what I'm shading right now. It doesn't extend into the page at all. So the blue here is A out, and the red is A in. Okay, so how do we calculate these? If we have, let's say that we know an outer radius and an inner radius. Then the area inside, the inner area, is pi r in squared. And the area of the outer surface is pi times the quantity r out squared minus r in squared. Okay, so Newton's second law says we have, the way I'm looking at this here with the x-axis pointing that way, we have pi r in squared times the pressure minus pi times the quantity r outer squared minus r inner squared times, you could, and actually let's not call that T. What should we call that? Well, what we should call that is, that's like a normal stress. So I'm going to call that sigma. Sigma is a stress or attraction. So if you multiply that by an area, you get a force. And so now we can do Newton's second law with these. So this is times sigma, and it's an equilibrium, so these add up to 0. You can divide everything by pi, and you get that sigma is equal to the pressure times the inner radius squared divided by the quantity r outer squared minus r inner squared. We could possibly simplify that a little bit. Yeah, leave it like that. Okay, so this is a normal stress. And what about the signs? So this is a normal stress in the outer material. In the shell. Is it plus or minus? We just sort of did this in absolute value. So what's happening in that material? Is it in tension or compression? It's in tension, so the sign is right the way we have it. And then second, notice that, so what causes, think about what would cause a shear stress in this outer material. If you looked at one little piece of this shell, you have an internal pressure pushing on it that way, and the adjacent piece, if we're talking about infinitesimals, the adjacent piece is pushing in the same direction with the same pressure. For a shear stress, we'd have to have those, we'd have to have external forces pushing like this, right? That's what a shear stress does. That's what a shear stress is. And so this is the total status of stress in the shell, in the outer material. Okay, so what do we know about the elements of the, well, let's think about, so now let's think about, like look at this from the back. And let's think about one stress element in there. Okay, and we'll use a coordinate system like this. Okay, so if we had cut this sphere, sort of what we did, if we cut it this way, the XX normal stress would be equal to this. Okay. Now, what if we cut it the other way to calculate the Y normal stress? What would happen then? I mean, it's a sphere, so it's the same in every direction, right? So this value is equal to the XX and the YY. So these are both equal to PR squared divided by our outer squared minus our inner squared. And these have to be in the plane of the surface. So this is with X and Y parallel to the surface. Z is perpendicular to the surface, so sigma ZZ is equal to 0 with Z perpendicular. So if you have a coordinate system that at a given point has the X, Y plane tangent to the sphere, and the Z-axis perpendicular to the surface, then the stress tensor is equal to sigma 0, 0, 0, sigma 0, 0, 0, 0, where sigma is equal to that thing we just had. So P times R inner squared divided by the quantity R outer squared minus R inner squared. Okay, so if you have, okay, first of all, why does it matter that this is thin-walled for our calculation? So this sort of goes back to the derivation of shear stress for thin-walled tubes. But does anyone remember what we used the thin wall assumption for?
Thin wall tubes.
We used it for that. Why was it? How did it come up in the derivation? So if you remember, yes, that's right. So if you have, as the walls get thinner and thinner, the stress tensor on the inside of the wall and the stress tensor on the outside of the wall are become equal to each other. So here we basically made the assumption that this stress tensor is the same everywhere, and we did that by saying that we knew what the total force was that normal stress had to. So the normal force had to all together integrate to provide this total force, but we didn't allow it to be different on the outside than the inside or whatever. So if the walls get too thick, you can have big variations in the normal stresses as you go across the wall. So we're assuming that that doesn't happen. What if you wanted to know the maximum shear stress? Yep, exactly. So the maximum shear stress, yep, and if all we want is the value, then we don't even care about that. So the maximum shear stress and this is already a principal stress tensor, so you know the principal stresses are sigma, sigma, 0. So the maximum shear stress is sigma minus 0 over 2. So P R inner squared over 2 times the quantity R outer squared minus R inner squared. Any questions about that? Okay, let's do this calculation now for like a tank, a cylindrical shape. And then once we have both of those, we'll do a couple problems, compare the total stresses, stuff like that. So a cylindrical vessel. So we have to take, so basically, if this is the object, we're only going to be looking at the stresses on the long side, but you can think of a stress element as an infinitesimal piece like this. For the same reason that we didn't have shear stresses in the spherical shape, we don't have any shear stresses here, but this time there's no reason to think that, you know, let's call this sigma xx, this sigma yy. This time there's no reason to think that those are going to be the same. Okay, so the first one, um, we'll do, so here's our free body. It's just half of this cylinder, so we're ignoring all this stuff. And again, we're going to include the fluid in this half. And let's say that, again, we have an inner radius and an outer radius. And so a free body diagram from the side. The fluid that we're not including in our free body is pushing on the fluid we are. So we have kind of the same thing going on that we did before. This is the pressure times the inner area. And that's being counteracted by tensile forces in the boundary. And so those are equal to, so let's choose a coordinate system with the x-axis along the long axis and the y-axis perpendicular. And the z-axis again is coming out of the surface. So this is going to be sigma xx times the area of that of the material that are cut. In a way, what I'm drawing here is a little misleading, I think, compared to what I usually do. This is really just one single force, but it's a continuous force that's happening all the way around. So this makes it look like we have two of those, but we don't. We really have a single one of these that's multiplied by a continuous area. And so Newton's second law says the pressure times pi times inner radius squared minus sigma xx times pi times the quantity r outer squared minus r inner squared is equal to 0. And so in this one, everything comes out the same way it did for the sphere. We have that sigma xx is equal to p times the inner radius squared divided by the quantity r outer squared minus r inner squared. So that's a tensile stress along the cylinder's long axis. And now we have to do the same thing for the y stresses. But this time, the calculation is going to be a little different. So this time, we're going to, like, you can think of it as a slice like this. Ooh, that looks awesome. Including all of the fluid inside there. And this length is L. And this is X. You know, it's along the long axis. Let me try to get that right. That's the x-axis. And the y-axis is this, the way I have it drawn. And so now I'm going to draw a free body diagram. This length is L. Okay, so free body diagram. Let's do it from the side view again. So we have half of the circle, and the inner part is applying a force that's equal to the pressure times the inner area. And counteracting that is the force at the outside. And this one really is this doesn't go all the way around, notice. This is just two strips, a strip along, like two thin rectangles, one along the top and one along the bottom. So this is sigma YY times the area top, and this is sigma YY times the area of that bottom rectangle. And if we're talking about a length L, then the second law says that inner rectangle, we'll call this the positive y direction. So the inner rectangle, we have the pressure times the That's right. So 2 times the inner radius times the length. And then the 2 forces that we have are, so this is sigma y times the thickness of the top. That's R outer minus R inner times L. And then minus another one of those. And all this is equal to 0. And so we can cancel length and the 2's. And we get that sigma y is equal to P times R inner over the quantity R outer minus R inner. Okay, so for a cylindrical shape, we have that the stress tensor is equal to what we got for the first one. So we have P R outer squared divided by the quantity R outer minus R inner. No, R outer squared minus R inner squared, sorry. And then we have 0, 0. And then our other one is P R inner divided by R outer minus R inner, 0. And then 0, 0, 0. Any questions about that? Okay, well, let's do the quiz, and then I'll do some problems with this on Wednesday.